Check, check, check. One, two, three. Okay. Good morning, good afternoon, good evening. Welcome back to another Coding Not So Every Day Until I Get a Job. This is day 135. And today we would like to continue with the practice of week 4. I think last time we were on volume and it was like almost a week ago. And there was a bit of an issue where I need to get a temporary monitor. It's totally unnecessary, but sort of like a I don't know. I guess I just couldn't do it with the second monitor, so I have to go to like Kleinanzeigen or like the eBay and find secondhand and cheap, relatively cheap monitor. So finally got it set up, finally get it working, and yeah, good to go. And let's God. Let's get straight into it. I think last time we already have uh I think we already saw the wait, is it the correct one? I think we already saw like the answer. I don't want please Copilot, do not like. God damn it. Okay. Hello. Hello, Andrew. Walaikum salam and Alfie. Hello, Andrew. Do you want to grab your shampoo or you want to just grab it tomorrow? Or I don't know. Up to you. Grab it tomorrow. Yeah, okay. It's okay. No worries, man. No worries. Please number of type. Tomorrow morning. Okay. It's okay. It's okay. Take your time. Yeah, let's try to do that. Um, do I have them? Yes. We're going very, very, what do you call it? Like very, very basic this time. Okay, sorry. So the F read is to, okay. Two types in particular will be useful when working with WAV files. UENT8 is a type that stores 8-bit. Unsigned, not negative integer, integers. Unsigned is not negative, yeah, unsigned, integer. We can treat each byte of WAV file's header as a unit value. INT6 is a type that stores 16-bit signed. We can treat each sample of audio in a WAV file as an int16t. Recall that WAV files header is always exactly 44-bit long. Note that volume C already defined a variable called... Okay, cool. Okay, so this fread file, this function reads data from a file that has been opened via fopen. It has an input pointer, which is the address of the first byte of memory into which to read the data. Sorry, I'm reading this slow because pointer still messes up my brain and the concept still hasn't really sorry, no pointer. Okay, sorry. Okay. Which is the pointer to a file return. Okay, stream. We have input as the file type, right? Or is it the... God damn it, I forgot how pointer works. Okay, I'm definitely gonna need to review that again because I am confused, not gonna lie. So we need to first create an int 16 die. Is it 16? Int 16, correct? Huh. Int 16 type called buffer. And while so it's gonna read it one by one, and is it like a, how would I say it? How would I explain it? Okay, that's correct. That's that. So it should be correct. Okay. I don't think we have pointer implementation on the volume. The real use case pointer is on recover. Okay. No, I mean like still the concept of the the pointer and how it works and the syntax with the all the new syntax and how it works. I just still haven't clicked. Let me grab my notes. I don't know if that would help, but Okay, they're actually I couldn't really test it because the WSL doesn't really have a. This is the terrible. Okay, let's just do the other problem. Okay, okay, let's just do the other problem. Oh no, let's just see if it compiles or not. Yeah, let's just see if it compiles. I'll take it. You know, if it compiles, I'll take it. GCC. It's volume. Let's see. Volume. Okay, it compiles. So at least let's try at volume. And then we can do input.wav. What is the testing? Let's just see if it just work or something. So we can just do input output.wav and let's do 0.5. And there is an output. Cool, but I don't think I could play audio on WSL. Or okay, I'm gonna need to redo the pointer. So okay, or maybe we could just pointers. Let's see. Okay, fine. Let's do W3 school. It's fine. Whatever it is. Okay. Oh, how do you test it? I do. I downloaded the whole thing, but I mean, it's fine if it's not working. A pointer is a variable that stores the memory address of another variable as its value. A pointer variable points to a data type of the same type and is created with the asterisk operator. The address of the variable you are working with is assigned to the pointer. Int, okay, I don't like this. I like this one, stick to this. Int my age. A pointer variable with name PTR stores the address of my age. Okay. Output the memory of my age pointer. So this one will have this. So okay, so basically this the ampersand is basically the fuck. The ampersand is the value. Okay, never mind. You can get the memory address of a variable using the reference or the ampersand, and a pointer is basically a variable that the value of that variable is the address of the variable. The memory address of my age with the pointer. Okay. Create a pointer variable that points to an int my age. Note that the type of the pointer has to match the type of the variable you're working with. Use the ampersand to store the memory address. To get the memory address, you can also get the value of the variable the pointer points to by using the reference operator. Okay, so if we use the asterisk, we can actually get the value itself. Okay. Okay. Which operator is used to get the value stored at the memory address a pointer is pointing to? The asterisk. Which of the following statement is correct about pointers in C? Pointers increase the size of variable. No, because it only points to the actual address, right? The memory line. Yeah. Because you will need pointers on many data structure, like for example, like this. Yes, yes. That's why I really want to get this part right. It's just that every single time I get confused by, okay, asterisks and then the ampersand, and then like, oh, when should I use the ampersand? When should I use the asterisk? I'm just okay. I understand the meaning that, okay, a pointer is just a variable that points to the address of another, like actually the which value of the pointer is the address of that variable, like actual address, like OX, the hexadecimal part in memory, right? But then like how would I know when to use the ampersand, the asterisk? I think I just need more practice, sort of like a more like example, so I could kind of like, oh, okay, you use this when you want to do that. I just don't know when or why or how. Okay, let's just switch. Okay, cool. Is there like a okay, we can just can we check the call stack like shorts? This is not a short, this is a 7-minute video. It's basically oh sorry, never mind.
If you saw our video on recursion, the process might have seemed a little bit magical, right? Like, how does a function know to wait for another function and pass its data to some other thing that's running at the same time? It can seem a little magical at the outset if you don't understand exactly how functions are called and operate in C. And the way they operate is using something called the call stack. And the way the call stack works is as follows. If you call a function, basically what happens is a big chunk of memory is set aside somewhere on the system for that function to do its work. So for example, if you call a function and the first thing you do is declare a couple of variables, what's gonna happen is a stack frame or a function frame will be created, a big chunk of memory, and those variables will be given space.
Wait, there's like this small videos. It's actually not small videos. I thought it was like actual YouTube shorts. Damn, wait, yeah, let me go back. The pointers, I wanna go back to the pointers, please. This is 30 minutes? Holy, okay. It's okay, I don't mind. As long as I can understand the material.
Here we are.
I'll take it.
This is probably going to be the most difficult topic that we talk about in CS50. And if you've read anything about pointers before, you might be a little bit intimidated going into this video. It's true that pointers do allow you the ability to perhaps screw up pretty badly when you're working with variables and data and causing your program to crash. But they're actually really useful, and they allow us a really great way to pass data back and forth.
I didn't know they have
that we're otherwise unable to
this.
do. And so what we really want to do here is train you to have good pointer discipline so that you can use pointers effectively to make your programs that much better.
Hey, yeah, the variable lives in the, well, it's not the actual memory, right? Because like the OS created the virtual memory for all those programs to run in those like blocks that the professor showed. But yeah, okay, I guess, you know what?
As I said, pointers give us a different way to pass data between functions. Now, if you recall from an earlier video when we were talking about variable scope, I mentioned that all the data that we pass between functions in C is passed by value. And I may not have used that term. What I meant there was that we are passing copies of data. When we pass a variable to a function, we're not actually passing the variable to the function, right? We're passing a copy of that data to the function. The function does what it will, and it calculates some value, and maybe we use that value when it gives it back. There was one exception to this rule of passing by value, and we'll come back to what that is a little later on in this video. If we use pointers instead of using variables, or instead of using the variables themselves or copies of the variables, we can now pass the variables around between functions in a different way. This means that if we make a change in one function, that change will actually take effect in a different function. Again, this is something we couldn't do previously, and if you've ever tried to swap the value of two variables in a function, you've noticed this problem sort of creeping up, right? If we want to swap x and y, and we pass them to a function called swap, inside of the function swap, the variables do exchange values. 1 becomes 2, 2 becomes 1, but we don't actually change anything in the original function, in the caller, because we can't. We're only working with copies of them. With pointers, though, we can actually pass x and y to a function. That function can do something with them, and those variables' values can actually change. So that's quite a change in our ability to work with data. Before we dive into pointers, I think it's worth taking a few minutes to go back to basics here and have a look at how computer memory works, because these two subjects are actually going to be pretty interrelated. As you probably know, on your computer system, you have a hard drive, or perhaps a solid-state drive, some sort of file storage location. It's usually somewhere in the neighborhood of 250 gigabytes to maybe a couple of terabytes now. And it's where all of your files ultimately live. Even when your computer is shut off, you can turn it back on, and you'll find your files are there again when you reboot your system. But disk drives, like a hard disk drive, an HDD, or a solid-state drive, an SSD, are just storage space. We can't actually do anything with the data that is in hard disk or in a solid-state drive. In order to actually change data or move it around, we have to move it to RAM, random access memory. Now, RAM, you have a lot less of in your computer. You may have somewhere in the neighborhood of 512 megabytes if you have an older computer, to maybe 2, 4, 8, 16, possibly even a little more.
Shorts is basic explanation of one topic, and they made sure the explanation clear. Like, this is what I've been looking for then. I thought it was like an actual YouTube shorts. Damn. A variable returns a value upon returns an address. Yeah, like, okay, that part I understand. It's just like, I don't know, or like, I don't have the intuition yet to kind of like, okay, this function uses the pointer, or this method uses the a reference using the ampersand. Like, I still don't have like the, how would I say it? Like the intuition, like, or the knowledge, like, I don't know when to use those thing yet. So yeah, I guess.
Gigabytes of RAM, so it's much smaller, but that's where all of the volatile data exists. That's where
Well, we know the RAM prices are going crazy, so having like 16 is so good.
Is destroyed. So that's why we need to have hard disk for the more permanent location of it, so that it exists. You know, it would be really bad if every time we turned our computer off, every file in our system was obliterated. So we work inside of RAM, and every time we're talking about memory, pretty much in CS50, we're talking about RAM, not hard disk. So when we move things into memory, it takes up a certain amount of space, not hard disk. So when we move things into memory, it takes up a certain RAM, not hard disk. So when we move things into memory, it takes up a certain amount of space. All the data types that we've been working with take up different amounts of space in RAM. So every time you create an integer variable, 4 bytes of memory are set aside in RAM so that you can work with that integer. You can declare the integer, change it, assign it to a value 10, increment it by 1, so on and so on. All of that needs to happen in RAM, and you get 4 bytes to work with for every integer that you create. Every character you create gets 1 byte. That's just how much space is needed to store a character. Every float, real number, gets 4 bytes, unless it's a double precision floating point number, which allows you to have more precise or more digits after the decimal point without losing precision, which take up 8 bytes of memory. Long longs, really big integers, also take up 8 bytes of memory. How many bytes of memory do strings take up? Well, let's put a pin in that question for now, but we'll come back to it. So back to this idea of memory as a big array of bite-sized cells. That's really all it is. It's just a huge array of cells, just like any other array that you're familiar with in C, except every element is 1 byte wide. And just like an array, every element has an address. Every element of an array has an index, and we can use that index to do so-called random access on the array. We don't have to start at the beginning of the array, iterate through every single element thereof to find what we're looking for. We can just say, I want to get to the 15th element or the 100th element, and you can just pass in that number and get the value you're looking for. Similarly, every location in memory has an address. So your memory might look something like this. Here's a very small chunk of memory. This is 20 bytes of memory. The first 20 bytes, because my addresses there at the bottom are 0, 1, 2, 3, and so on, all the way up to 19. And when I declare variables, when I start to work with them, the system is going to set aside some space for me in this memory to work with my variables. So I might say char c equals capital H. And what's going to happen? Well, the system is going to set aside for me 1 byte. In this case, it chose byte number 4, the byte at address 4, and it's going to store the letter capital H in there for me. If I then say int speed limit equals 65, it's going to set aside 4 bytes of memory for me. It's going to treat those 4 bytes as a single unit because what we're working with is an integer here, and it's going to store 65 in there. Now, already I'm kind of telling you a bit of a lie, right? Because we know that computers work in binary. They don't understand necessarily what a capital H is or what a 65 is. They only understand binary, zeros and ones. And so actually what we're storing in there is not the letter H and the number 65, but rather the binary representations thereof, which look a little something like this. And in particular, in the context of the integer variable, it's not going to just spit it into, it's not going to treat it as one 4-byte chunk necessarily. It's actually going to treat it as 4 1-byte chunks, which might look something like this. And even this isn't entirely true either because of something called endianness, which we're not going to get into now, but if you're curious about, you can read up on little and big endianness. But for the sake of this argument, for the sake of this video, let's just assume that that is in fact how the number 65 would be represented in memory on every system, although that's not entirely true. But let's actually just get rid of all the binary entirely and just think about it as H and 65. It's a lot easier to think about it like that as a human being. All right, so it also seems maybe a little random that my system didn't give me bytes 5, 6, 7, and 8 to store the integer. There's a reason for that too, which we won't get into right now, but suffice it to say that what the computer is doing here is probably a good move on its part to not give me memory that's necessarily back-to-back, although it's going to do it now if I want to get another string called surname and I want to put Lloyd in there. I'm going to need to fit one character. Each letter of that's going to require one character, one byte of memory. So if I can put Lloyd into my array like this, I'm pretty good to go, right? What's missing? Remember that every string we work with in C ends with \0, and we can't omit that here either. We need to set aside one byte of memory to hold that so we know when our string has ended. And so again, this arrangement of the way things appear in memory might be a little random, but it actually is how most systems are designed, to line them up on multiples of 4, for reasons, again, that we don't need to get into right now. But this, so suffice to say, after these 3 lines of code, this is what memory might look like. If it assigned me memory locations 4, 8, and 12 to hold my data, this is what my memory might look like. And just to be particularly pedantic here, when we're talking about memory addresses, we usually do so using hexadecimal notation. So why don't we convert all of these from decimal to hexadecimal notation, just because that's generally how we refer to memory. So instead of being 0 through 19, what we have is 0x0 through 0x13. Those are the 20 bytes of memory that we're looking at in this image right here. So all of that being said, let's step away from memory for a second and back to pointers. Here's the most important thing to remember as we start working with pointers. A pointer is nothing more than an address. I'll say it again because it's that important. A pointer is nothing more than an address. Pointers are addresses to locations in memory where variables live. Knowing that, it becomes hopefully a little bit easier to work with them. Another thing I like to do is to have sort of diagrams visually representing what's happening with various lines of code. And we'll do this a couple of times in pointers and when we talk about dynamic memory allocation as well, because I think that these diagrams can be particularly helpful. So if I say, for example,
and present it as the memory address and a variable, which is the value at the memory address.
I like to think about it like a box. I have a box, and it's colored green because I can put integers in green boxes. If it was a character, I might have a blue box. But I always say, if I'm creating a box that can hold integers, that box is colored green. And I take a permanent marker and I write K on the side of it. So I have a box called K into which I can put integers. So when I say int K, that's what happens in my head. If I say K equals 5, what am I doing? Well, I'm putting 5 in the box, right? This is pretty straightforward. If I say int K, create a box called K. If I say K equals 5, put 5 into the box. Hopefully that's not too much of a leap. Here's where things get a little interesting, though. If I say int star PK, well, even if I don't know what this necessarily means, it's clearly got something to do with an integer. So I'm going to color this box greenish. I know it's got something to do with an integer, but it's not an integer itself because it's an int star. There's something slightly different about it. So an integer is involved, but otherwise it's not too different from what we were talking about. It's a box. It's got a label. We're going to label this one PK, and it's capable of holding int stars, whatever those are. They have something to do with integers, clearly. Here's the last line, though. If I say PK equals ampersand K, whoa, what just happened, right? So this random number, seemingly random number, gets thrown into the box there. All that is PK gets the address of K. So I'm sticking where K lives in memory, its address, the address of its bytes. All I'm doing is I'm saying that value is what I'm going to put inside of my box called PK. And because these things are pointers, and because looking at a string like 0x80c74820 is probably not very meaningful, when we generally visualize pointers, we actually do so as pointers. PK gives us the information we need to find K in memory. So basically, PK has an arrow in it, and if we walk the length of that arrow, imagine it's something that you can walk on. If we walk along the length of the arrow, at the very tip of that arrow, we will find the location in memory where K lives. And that's really important because once we know where K lives, we can start to work with the data inside of that memory location. We're getting a teeny bit ahead of ourselves for now. So what is a pointer? A pointer is a data item whose value is a memory address. That was that 0x80 stuff going on. That was a memory address. That was a location in memory. And the type of a pointer describes the kind of data you'll find at that memory address. So there's the int star part, right? If I follow that arrow, it's going to lead me to a location. And that location, what I will find there, in my example, is a green colored box. It's an integer. That's what I will find if I go to that address. So the data type of a pointer describes what you will find at that memory address. So here's the really cool thing, though. Pointers allow us to pass variables between functions and actually pass variables and not pass copies of them. Because if we know exactly where in memory to find a variable, we don't need to make a copy of it. We can just go to that location and work with that variable. So in that sense, pointers sort of make a computer environment a lot more like the real world, right? So here's an analogy. Let's say that I have a notebook, right? And it's full of notes, and I would like you to update it. You are a function that updates notes, right? In the way we've been working so far, what happens is you will take my notebook, you'll go to the copy store, you'll make a Xerox copy of every page of the notebook, you'll leave my notebook back on my desk when you're done, you'll go and cross out things in my notebook that are out of date or wrong, and then you'll pass back to me the stack of Xerox pages that is a replica of my notebook with the changes that you've made to it. And at that point, it's up to me as the calling function, as the caller, to decide to take your notes and integrate them back into my notebook. So there's a lot of steps involved here, right? Like, wouldn't it be better if I just say, hey, can you update my notebook for me, hand you my notebook, and you take things and literally cross them out and update my notes in my notebook, and then give me my notebook back? That's kind of what pointers allow us to do. They make this environment a lot more like how we operate in reality. All right, so that's what a pointer is. Let's talk about how pointers work in C and how we can start to work with them. So there's a very simple pointer in C called the null pointer. The null pointer points to nothing. This probably seems like it's actually not a very useful thing, but as we'll see a little later on, the fact that this null pointer exists actually really can come in handy. And whenever you create a pointer and you don't set its value immediately, an example of setting its value immediately would be a couple slides back where I said pk equals ampersand k. pk gets k's address, as we'll see what that means. We'll see how to code that shortly. If we don't set its value to something meaningful immediately, you should always set your pointer to point to null. You should set it to point to nothing. That's very different than just leaving the value as it is, and then declaring a pointer and just assuming it's null, because that's rarely true. So you should always set the value of a pointer to null if you don't set its value to something meaningful immediately. You can check whether a pointer's value is null using the equality operator equals equals, just like you can compare any integer values or character values using equals equals as well. It's a special sort of constant value that you can use to test. So that was a very simple pointer, the null pointer. Another way to create a pointer is to extract the address of a variable you've already created. And you do this using the ampersand operator, address extraction, which we've already seen previously in the first diagram example I showed. So if x is a variable that we've already created of type integer, then ampersand x is a pointer to an integer. Ampersand x is, remember, ampersand is going to extract the address of the thing on the right. And since a pointer is just an address, then ampersand x is a pointer to an integer whose value is where in memory x lives. It's x's address. So ampersand x is the address of x. Let's take this one step further and connect to something I alluded to in a prior video. If ARR is an array of doubles, then ampersand ARR square bracket I is a pointer to a double. Okay? ARR square bracket I, if ARR is an array of doubles, then ARR square bracket I is the ith element of that array. And ampersand ARR square bracket I is where in memory the ith element of ARR exists. So what's the implication here? An array's name, the implication of this whole thing, is that an array's name is actually itself a pointer. You've been working with pointers all along every time that you've used an array. Remember from the example on variable scope. Near the end of the video, I present an example where we have a function called setInt and a function called setArray, and you're challenged to determine whether or not, or what the values will be printed out at the end of the function, at the end of the main program. If you recall from that example, or if you've watched the video, you know that when the call to setInt effectively does nothing, but the call to setArray does. And I sort of glossed over why that was the case at the time. I just said, well, it's an array, it's special, there's a reason. The reason is that an array's name is really just a pointer. And there's this special square bracket syntax that make things a lot nicer to work with, and they make the idea of a pointer a lot less intimidating, and that's why they're sort of presented in that way. But really, arrays are just pointers, and that's why when we made a change to the array, when we passed an array as a parameter to a function or as an argument to a function, the contents of the array actually changed in both the callee and in the caller, which for every other kind of variable we saw was not the case. So that's just something to keep in mind when you're working with pointers, is that the name of an array is actually a pointer to the first the case. So that's just something to keep in mind when you're working with pointers, is that the name of
the array
is actually a pointer to the first element of that array. Okay, so now we have all these facts. Let's keep going, right? Why do we care about where something lives? Well, like I said, it's pretty useful to know where something lives so you can go there and change it, work with it, and actually have the thing that you want to do to that variable take effect and not take effect on some copy of it. This is called dereferencing. We go to the reference and we change the value there. So if we have a pointer and it's called PC and it points to a character, then we can say star PC. And star PC is the name of what we'll find if we go to the address PC. What we'll find there is a character, and star PC is how we refer to the data at that location. So we could say something like star PC equals capital D or something like that. And that means that whatever was at memory address PC, whatever character was previously there, is now capital D if we say star PC equals capital D. So here we go again with some weird C stuff, right? So we've seen star previously as being somehow part of the data type, and now it's being used in a slightly different context to access the data at a location. I know it's a little confusing, and that's actually part of this whole why pointers have this mythology around them of being so complex. It's kind of a syntax problem, honestly. But star is used in both contexts, both as part of the type name, and we'll see a little later something else too, and right now is the dereference operator. So it goes to the reference. It accesses the data at the location of the pointer and allows you to manipulate it at will. Now this is very similar to visiting your neighbor, right? If you know where your neighbor lives, you're not hanging out with your neighbor. You happen to know where they live, but that doesn't mean that by virtue of having that knowledge, you are interacting with them. If you want to interact with them, you have to go to their house. You have to go to where they live. And once you do that, then you can interact with them just like you'd want to. And similarly with variables, you need to go to their address if you want to interact with them. You can't just know the address. And the way you go to the address is to use star, the dereference operator. What do you think happens if we
section video? It's on our additional lecture. The video focuses on hands-on practice. If you want additional, you can watch. Oh, okay. Yeah, definitely.
Null. Recall that the null pointer points to nothing. Right. So if you try and dereference nothing or go to an address nothing, what do you think happens? Well, if you guess segmentation fault, you'd be right. If you try and dereference a null pointer, you suffer a segmentation fault. But wait, didn't I tell you that if you're not going to set your value of your pointer to something meaningful, you should set it to null? I did, and actually the segmentation fault is kind of a good behavior. Have you ever declared a variable and not assigned its value immediately? So you just say int x, semicolon. You don't actually assign it to anything, and then later on in your code you print out the value of x having still not assigned it to anything? Frequently you'll get 0, but sometimes you might get some random number and you have no idea where it came from.
Array
Similarly, things happen
top
with
and
pointers.
array
When you
push
declare a
is like
pointer,
implementation
int
of
star
pointers
pk,
on
for example, and you don't assign it
JS.
to a value, you get 4 bytes of memory. You have 4 bytes of memory in the system
Yeah, that
you
makes
find
sense.
that have some meaningful
That's
value.
why you can
And
change
there might have been something
the
already
value
there
or
that
add,
is no
right?
longer needed by another function, so you
Because
just have
it's
whatever data was
just
there. What if you tried to dereference some
the
address that
actual
you don't,
memory
there were
of
already bytes and
of course,
information in there,
JavaScript
that's now in
works
your pointer. If you try and dereference that pointer,
differently,
you might be messing with
right?
some memory that you didn't intend to mess with at all. And in fact, you could do something really devastating, like break another program or break another function or do something malicious that you didn't intend to do at all. And so that's why it's actually a good idea to set your pointers to null if you don't set them to something meaningful. It's probably better at the end of the day for your program to crash than for it to do something that screws up another program or another function. That behavior is probably even less ideal than just crashing. And so that's why it's actually a good habit to get into, to set your pointers to null if you don't set them to a meaningful value immediately, a value that you know and that you can safely dereference. So let's come back now and take a look at the overall syntax of the situation. If I say int star p semicolon, what have I just done? What I've done is this. I know that the value of p is an address, because all pointers are just addresses. I can dereference p using the star operator. In this context here at the very top, recall, the star is part of the type. It's int star is the data type. But I can dereference p using the star operator. And if I do so, if I go to that address, what will I find at that address? I will find an integer. So int star p is basically saying p is an address. I can dereference p, and if I do, I will find an integer at that memory location. Okay, so I said that there was another annoying thing with stars, and here's where that annoying thing with stars is. Have you ever tried to declare multiple variables of the same type on the same line of code?
Yeah.
So for a second, pretend that the code I actually have there in green isn't there, and it just says int x, comma y, comma z, semicolon. What that would do is actually create 3 integer variables for you, one called x, one called y, and one called z. It's a way to do it without having to split it onto 3 lines. Here's where stars get annoying again, though, because the star is actually part of both the type name and part of the variable name. And so if I say int star px, comma py, comma pz, what I actually get is a pointer to an integer called px and 2 integers, py and pz. And that's probably not what we want. That's not good. So if I want to create multiple pointers on the same line of the same type, int stars, what I actually need to do is say int star pa, comma star pb, comma star pc. Now, having just said that, and now telling you this, you probably will never do this. And it's probably a good thing, honestly, because you might inadvertently omit a star or something like that. It's probably best to maybe declare pointers on individual lines. But it's just another one of those annoying syntax things with stars that make pointers so difficult to work with, because it's just the syntactic mess you have to work through. With practice, it does really become second nature. I still make mistakes with it, still after programming for 10 years. So don't be upset if it's something that happens to you. It's pretty common, honestly. It's really kind of a flaw of the syntax. Okay, so I kind of promised that we would revisit the concept of how large is a string. Well, if I told you that a string, we've really kind of been lying to you the whole time. There's no data type called string. And in fact, I mentioned this in one of our earliest videos on data types, that string was a data type that was created for you in CS50.h. You have to pound include CS50.h in order to use it. Well, string is really just an alias for something called a char star, a pointer to a character. Well, pointers, recall, are just addresses. So what is the size in bytes of a string? Well, it's 4 or 8.
Sorry. I have a sudden message. Let's go back.
Not what we want. That's not good. So if I want to create multiple pointers on the same line of the same type, int stars, what I actually need to do is say int star pa, comma star pb, comma star pc. Now, having just said that, and now telling you this, you probably will never do this. And it's probably a good thing, honestly, because you might inadvertently omit a star or something like that. It's probably best to maybe declare pointers on individual lines. But it's just another one of those annoying syntax things with stars that make pointers so difficult to work with, because it's just the syntactic mess you have to work through. With practice, it does really become second nature. I still make mistakes with it, still after programming for 10 years. So don't be upset if it's something that happens to you. It's pretty common, honestly. It's really kind of a flaw of the syntax. Okay, so I kind of promised that we would revisit the concept of how large is a string. Well, if I told you that a string, we've really kind of been lying to you the whole time. There's no data type called string. And in fact, I mentioned this in one of our earliest videos on data types, that string was a data type that was created for you in CS50.h. You have to pound include CS50.h in order to use it. Well, string is really just an alias for something called a char star, a pointer to a character. Well, pointers, recall, are just addresses. So what is the size in bytes of a string? Well, it's 4 or 8. And the reason I say 4 or 8 is because it actually depends on the system. If you're using CS50 IDE, char stars, the size of a char star is 8. It's a 64-bit system. Every address in memory is 64 bits long. If you're using CS50 Appliance or using any 32-bit machine, and you've heard that term 32-bit machine, what is a 32-bit machine? Well, it just means that every address in memory is 32 bits long. And so 32 bits is 4 bytes. So a char star is 4 or 8 bytes depending on your system. And indeed, any data types, and a pointer to any data type, since all pointers are just addresses, are 4 or 8 bytes. So let's revisit this diagram, and let's conclude this video with a little exercise here. So here's the diagram we left off with at the very beginning of the video. So what happens now if I say star pk equals 35? So what does it mean when I say star pk equals 35?
You're going to change the vibe into 35, right?
In context here, star is dereference operator. So when the dereference operator is used, we go to the address pointed to by pk, and we change what we find. So star pk equals 35 effectively does this to the picture. So it's basically syntactically identical to having said k equals 35. One more. If I say int m, I create a new variable called m, a new box. It's a green box because it's going to hold an integer, and it's labeled m. If I say m equals 4,
It's gonna
I put an
put the
integer
4.
into that box.
Yeah.
If I say pk equals ampersand m, how does this diagram?
PK, it's going to be another. Wait, no. Would it be the same, or do you still need the star?
Change. PK.
No. This one will point
M.
into
Recall what the
this
ampersand
memory.
operator does or is called. Remember that ampersand, some variable name, is the address.
So it's
of the
gonna.
variable name.
This
So
is gonna
always
go
PK
here.
gets the address of m. And so effectively, what happens in the diagram is that PK no longer points to k.
Let's point to M.
Points to m.
Yes. Okay.
Again, pointers are very tricky to work with, and they take a lot of practice. But because of their ability to allow you to pass data between functions and actually have those changes take effect, getting your head around them is really important. It probably is the most complicated topic we discuss in CS50, but the value that you get from using pointers far outweighs the complications that come from learning them. So I wish you the best of luck learning about pointers. I'm Doug Lloyd. This is CS50.
Thank you. Okay, let's see. What is it called? Section video, right? This one. Okay, I want to check the official YouTube. Does it have like a, okay, it doesn't have like a.
Hi everyone, my name is Julia and this is CS50 Week 4 Sections, and today we're talking about all things memory. I am a preceptor here on Harvard campus, and it is very lovely to see you all here in the room. So today we're talking all things memory, and that includes pointers, file I/O. We're going to get some practice with how to operate these weird pointers things, and also some practice with how to open files, write into them, and read information from them. That should really help you on this week's project.
Doesn't have like a.
So let's jump right ahead.
Chapters?
Let's talk about pointers first. So you might recall from week 1, we talked about a phone book, right? We set it up with different variables, such as calls that we try to keep track of the, for example, how many times your mom or your friend called you. So let's just get a quick refresher on that. So as in week 1, we had our variable called int calls, that is of type int. And lastly, we have ampersand x that takes x, not, it doesn't necessarily come up with the using int star p.
Okay, here we go. Pointers
Is
practice.
really getting practice with pointers and understanding how to correspond these things all together. So let's consider this variable x that we're setting equal to 4. And so as before, we can't visualize it, right? We're creating this new box that has value 4 and some address. For the sake of the exercise, I came up with a fake one, but it'll certainly look different when you're trying to print out addresses in your computer. Next, let's create a pointer, right? So as before, the way that we define it is using int star p equals address of x. And as before, you can visualize this box, right, that stores the address of x. Notice how the two values correlate. Next, let's print out something, right? So this is where this magical connection comes in. So as I said before, when we use star p, that means that we're grabbing the address that is stored in our pointer and then accessing the value stored in that address. And so consequently, what we'll see in the terminal is, and you can type in the chat, if I'm printing out print f quote unquote %i comma star p. Yes, so in our terminal we will see 4, because as I just said, what is happening is we're grabbing that address, we're going to the location of that address.
Sorry, I already answered. I forgot to mute the mic. But yeah, it's gonna do 4 because
so
it's the reference with the
sort of
asterisk
we
p.
could have done with the previous slides, but let's push it a little further. So consider I want to change my value. So one way to do it is certainly just changing the value of x, but now that I have my pointers, I can also do it in this way. By using star p and setting it to 2, what is going to happen is I'm going to change the value of x.
To
and
2.
now it is going to be equal to 2. Because as before, right, was the line 3, when we printed out the value, we used star p.
Implementable.io on PDF. Okay, let's do that. You know, I don't mind
so now our
taking like
that is the value that's
a week
there.
or a longer time to understand this, because
star p minus
why not?
2, what would that be?
I have nothing else to do.
What is the value that we're going to see in the terminal now? Exactly. It
Okay, so it's going to be 0.
will be 0, right? Because the new value that I have in x is 2. I am subtracting 2, so I'm printing out 0 in the terminal. But will that change my value of x? Like, am I subtracting x minus 2, and now the value of x is 0 as well? Right, so someone in the chat said no. I'm not explicitly changing x or even star p. I'm just printing that value out. Okay, so let's keep moving. And what we're going to print out last is x, right? So now that we've changed that value to 2, what we're going to see in the terminal exactly is 2. So using these pointers and the connection that we have between the addresses, we can now manipulate things even better. So, right, I don't have to like explicitly change values in my variables. I can reference them using pointers and then access that information through the addresses that connect the two, okay? So before we jump to file IO and switch gears a little bit, what questions do we have about this exercise and pointers? Yeah, so someone asked to explain the code. So let's walk through it line by line again. So in the very beginning, we have int x equals 4, right? That is creating this new variable. Then we need to set up our pointer, right? And as we just talked about, pointers to our addresses. So using the ampersand, we're grabbing that address of x, right? Like we're grabbing this hex value that is like signifying the address of x. Then our printf line, right? Like we've seen it a dozen of times so far. And to achieve the same result, I could have just said printf %i x, but I'm using the power of pointers to just reference that value and print it out here on line 3. Again, harnessing like the power of pointers and being able to reference the values without explicitly changing them. Well, in this case we are, but on the 4th line, right, where we're using star p equals 2 is where we're changing the value of x, and now it is 2. And then again, on those last 2 printf lines, we are just printing out different things, right, just for practice to see what we'll actually see in the terminal combined to what actually is stored in those variable cells. So let me go back to the chat.
So, okay,
again,
the thing is, where is the, okay, so there's some people created like the, okay, critical, no, since the input, okay. I usually imagine pointers as variables that have an arrow pointing to another location. Like this one, right?
So someone that's changing the value of the pointer, change the value of the variable permanently. So in this case, yes, right, because we went explicitly to the location of this variable and we changed the value to 2. For example, on line, 5, when we printed out star p minus 2, we just used that value, right, and subtracted 2. Okay. So why didn't the last value change from 0 to 2? So on line 5, right, where we're printing out star p minus 2, we're not explicitly changing the value of x, right? We are just using that value by referencing the pointer and subtracting 2 from it. Okay. Let's keep moving forward for the sake of time, but I'll try to get some of my questions in the end of the section. File.io, right? So this is where why we need pointers comes in, right? So the things I just talked about, you could try to do that with just the variables that we knew, but with the files, this is where the pointers come really in handy, and this is what will enable us to do more complicated things that, frankly, we could do before. So to get us started, here are 2 of the key functions that we will use in the beginning. So the first one is fopen. This will allow us to open a file to either read or write into it. As I mentioned briefly just a few minutes ago, it is really important to close those files, right? So if we fopen anything like a file called input or a file called output, we must close it after we're done with it. So this is a really good practice to get into. Anything you fopen, make sure you close it, because again, we're going to run into these memory issues and weird errors that might be difficult to solve. So making sure that you have this like very like explicit like approach of how you handle the code is very important. Okay. Yeah, someone's mentioning malloc in the chat. So this is, again, where all these like errors come in. So we're not going to talk about malloc function a lot during this section, but malloc can be used to create memory, right? Like if we want to allocate some memory for us to use, but it's really important to free that memory that you allocated and use to go back to the computer so that we don't run into any memory errors. So let's consider this file. So for example, I have a txt file that has hi in it, and it is stored at some address. Well, how could I use it, right? Like how can I open it? How can I read from it or write into it? I can use my function called fopen. And again, it's like, whoa, like things escalated really quickly, right? There's like so much stuff going on, the stars, the capitalization, like all the other arguments. So let's parse it one by one. So the first thing that we have is the name of the variable, right? Again, variable names can be anything that you want. So in this case, I chose input, but it could also be file or text or word, right? It is up to you as a programmer what variable names you want to use. Then with every variable definition comes the type, right? So in this case, our type is a pointer to file, right? So we've seen int star, we've seen char star. File star is again very similar, but someone just like went ahead and like defined what like file is, and it's literally these like txt files or any other files, right? And so as before, our pointers store the address, right? So on the bottom of my txt file right here, I have its address. So what the input is actually going to store is the address of this file. And the way I could get that address is by using the fopen function, right? So when I use fopen, what it will return is the address of the file that I am trying to access. Well, let's parse fopen one by one as well. First argument is the file name, right? So hi.txt or test PDF, right? It can be whatever file you want to use. Then the next argument is the mode, right? So in this case, what we want to do is just read from the file that we opened. so we're using R, short for read. If we want to modify the file, right, or write something into it, the word we can use is W. And I believe in this week's lecture, Professor Malin also defined something that like RB and WB, that is for reading or writing binary files, right? Explicitly saying that the sort of like the bits of the pieces of data that you're reading are binary, so like no need to try to like interpret it or understand what it is, right? So we have this setup. We've opened our file. We now have the address of our txt. What is going on next? Well, as before, there's an arrow, right? So again, we're going back to these diagrams and we're drawing things, but essentially what the input does, it is a pointer to the address where this txt file is stored. So you can imagine, again, the arrow that points to it. Okay, now that we've opened our file, what can we do with it? So two key functions that we will talk about today and this week in general is fread, that will read data from a file, fwrite, that will write data from a buffer to a file. And what is a buffer? And we're going to talk about in just a second, but you can imagine it is just a chunk of memory that can temporarily store some data from the file. And there's a little hint of the question I'm going to ask you in just in 2 minutes, so you might think about it already, but why do we need the buffer, right? Like, why do we want to use it? So let's go back to our setup. We have this txt file that is storing hi, right, or any other text. What it actually is just collection of some pieces of data, right? So like collection of some bytes. So how do we actually read from it? There's a very, in this case, this is what we're going to do, but there's a very like methodic approach of how you want to read your data. Let's start from the end. So the very last argument in our fread function is location to read from. So this is the new file that you open, like the file where you want to grab the information from and read it from there. So you can imagine it almost like a little dot or like a cursor that's showing you where this file is. Then next two parts is the size of blocks to read in bytes, and the in bytes part is important, right? Because in this case, I'm just reading size of 1 byte, but if you want to read something different, for example, if it is more than 1 byte, and like maybe you don't know exactly like, oh, like is that variable like 2 bytes or 3 bytes, a handy function to use is size of, because also depending on what machine you're using, for example, integer can be actually different size depending on the machine, and by using the size of function, you can always get the precise number. Next component of our fread function is how many blocks we want to read, right? So in this case, I want to read 4 blocks of 1 byte, right? So 4 blocks on 1 byte, and you can once again visualize it by sort of like allocating or highlighting these 4 squares in our text file. And lastly is the location to store blocks in, right? So in this case, it is buffer, and we're going to grab these 4 bytes from our input file, right, from hi.txt, and then store it in the buffer variable. And because I know that I'm going to read 4 blocks of size of 1 byte, I can pre-allocate that memory and have my buffer be ready to accept those bytes. So once again, this is the fread function that we'll use in this case, and to have sort of like an algorithm to it, this is how you can visualize it, right? So if we have fread, our function, the first argument will be stored to where, right? Into buffer, or whatever other variable name you come up with. Again, this is arbitrary. How many blocks and on what size? So 4 blocks of size 1, and here I am flipping it a little bit, right, from what we saw before, but it is essentially size of 1 byte 4 times almost. And then from where, right? From the input file, or again, whatever name you chose to give to your input file. So again, to where, how many and on what size, and then from where. This is how we put our fread function together, and this is how we can visualize it in the end, right? We had our pointer input to the file that we were interested in. We grabbed 4 bytes from there, and then we stored it into buffer. So now input is pointing to the next bytes in our txt file. Okay. So this was reading information. How do we okay, that was reading information, but why were we using buffer in the first place, right? Like I promised you to come back to that question, and now we're back to it. Why were we using buffer in the first place, right? Like why could I not have just done like fread from input to output and be done with it? Why it is important to use buffer? Why do we want to use buffer in this case? If anyone want to type their suggestions or thoughts. Okay, yeah, so to store it, yeah, we want to like store something in buffer. Temporary storage of data. Okay, memory, right, is a big consideration. There's one more thing. Yeah, someone said it's like a third glass from the lecture, so it's like our temporary variable that we're creating. So often we don't know where the data ends, right? So I can say like read 200 bytes, right? What if there are more bytes? Or what if there are not as many bytes? And by ensuring that we're doing just like little bits at a time, right? Maybe like 4 bytes at a time, even 1 byte at a time until we reach the end, is why buffer is important, right? Like we're using this like third class, as we talked about in like numerous swapping variables, like we're using this like third class, third variable to be a temporary storage as we're sort of like moving things alone, okay? So that's why buffer is important. That's why you will find using, you'll find using buffer a lot this coming week to sort of like temporarily store information. But now that we've learned how to fread, let's talk about fwrite, right? So we not only just want to open information, we also want to make sure we know how to modify it. So the syntax is again very similar, but just slightly different. And let's go through it one by one. So with fwrite, the first argument that I have is from where, right? So contrary to fread, we're sort of like flipping things here. So first, from where, I want to write from buffer. Again, how many and what size? Well, in this case, 4 blocks of size 1. And then the last bit is
okay. Can we just
fwrite blocks of size 4 bytes is the day. What questions do we have about fread or fwrite, or how we were handling these pieces? Yeah, so someone asked to explain exactly what the blocks are. So if you open like a PDF file, right, or like a text file, you see text on the page, right? That is what's visible to the humans. But what is going on behind is like some sequence of like bytes, right? So this is how we like sort of handle these documents on like a micro level. We like go a level further and we say, okay, I want to read 1 byte at a time. It might be like, I don't know, a character or just like if we're looking at an image, like it'll be something different, right? But it'll be 1 byte at a time. And again, by splitting the problem in these like smaller pieces, we can ensure that we're actually like getting through the entire file versus just like, let's read 200 bytes, right? Like maybe that's too much, maybe that's not enough. We want to make sure we're handling it bitwise. Okay, let's see. Yeah, so someone said fread is like copying some bytes from another file and transferring it to another file. Exactly. By using fread, I'm not changing my hi.txt, right? It is staying the same. Like I'm not taking things away. I'm just copying it or like referencing that file to read things into buffer. So if I go back a little back on my slides, right? So I moved my arrow 4 blocks forward, but they didn't necessarily disappear, right? Like those
just
4 blocks
reading them
in my TXT
or like
file,
copying them into the buffer
like I'm moving forward, right? Like I
before
bytes,
putting
so
into
I
the
can go
output,
on to read the
right?
next ones.
Right?
Okay.
Is there like a practice question after this? Like a okay, yeah. Oh yeah, there is a okay practice. Let's try that.
Okay. So someone asked to see the fwrite side again, and I can go back to that. Okay, it's right here. So right, this is fwrite.
To where
but
the
let's
amount
go
of
ahead and get some practice with these guys, right?
yeah
so
yeah
fwrite and
practice
files.
please.
So on the menu today is the activity. So on the menu today is the activity that will allow us to detect PDF files, right? So what we're going to do is we're going to create a program called pdf.c. And again, you're welcome to follow along with me or reference it after this, but we will write a program that will read the file and then we'll try to understand if it's a PDF or not. A helpful hint here is that all PDFs begin with a specific 4-byte sequence. And if you do some math manipulation, you're welcome to figure out what exactly that is. But the example usage of the program is that when we run this PDF program and we plug in a specific file name, it should let it should let us know if it's a PDF or not. Okay? So
would it just
let's move to csrt.dev. And I already
if fread and it's like the first like
okay
0 to 3rd buffer equals to those, it's gonna print yes, return yes. It's gonna take the argument, right? Yeah.
So I already pre-wrote some code just to help myself move along. So let's walk through it together line by line of all the to-dos that we need to do. So first, and I gave a little hint here.
Check usage. It's similar to a lot of the code. Like
so
if the arg is over than 2, it's gonna return 1.
We are telling users exactly how many variables, like how many CLAs we're expecting from them, and exactly what we want to see. Next, we're going to open that file that the user gave us. We're going to create buffer for that file, right? So again, we want to store just a little bit of it. We're going to create an array of signature bytes, right? So the signature bytes is exactly the 4-byte signature.
Or using like the array copy, store copy.
Right? So looking at the first 4 bytes of our file, and then at the 4 signature bytes that we define in our array, we're going to compare them.
Yeah.
And then if they all match up, then it's indeed a PDF. And if not, it's not a PDF file. And in the end, a very important thing we're going to do is we're going to close the file, right? Because we opened it in the very beginning, and we want to make sure that we close it back again. Okay, so let's get started. And I'm going to again skip this comment just a second to show what happens if you don't check for CLAs. But let's start writing some code. So as we just saw on the slides, the way that we open file, the way we can use files, right, is by using the pointers. So the type that we're going to point to is file. this asterisk is what gives us a pointer, and I'm going to call my file input. I'm going to use fopen, and inside of fopen, I'm going to use my command line arguments to access the file name, right? So per usage right here, what we want to see from the user is ./pdf to run the program, but then the file name, which will be our second command line argument. And I'm opening in mode read, right? Because I don't want to modify anything in it. I just want to make sure I'm grabbing the information that I need, and that is it, okay? Next, I'm going to create buffer for that file, right? For the little bits of information that I'm going to read. And so I'm going to introduce something new, and it is uint8_t buffer. Okay? So the tricky thing in this whole line is just this guy, right? Buffer is just the variable name that I picked. For it is just defining that we will have 4 little cells in our array. But what is uint8_t? Does anyone know what that is? And it's okay if you don't. But yeah, so very close. Someone in the chat says, I believe it's a byte. Very close. It is a size of byte, but it actually is an unsigned integer, right? So first of all, it is making sure that we only have non-negative values, but also making sure that it's exactly 1 byte. As I mentioned before, depending on what machine you're using, integers can actually be bigger or smaller, but by using uint8_t, we're always ensuring that it is of size byte, right? Okay, now let's create another array where we're going to store our signature bytes. So this is what is going to help us identify if it is a PDF. And I have the signature bytes pre-written, so I'm just going to copy them over. Okay, so this will help us identify if it's a PDF, right? So it is just the 4 bytes that are always contained in the beginning of each PDF. And so by comparing what it will actually read from the file, we will be able to identify that. Okay. So this is where the tricky part comes in, right? Like all of these things that we sort of knew, like how to define arrays, fopen was a little bit new to us, but now is the interesting part, right? Like we want to read first 4 bytes from the file. And by looking at this keyword right here, I see that I'll probably use fread, right? And I mentioned in the beginning that we don't want to modify anything, but can you all help me out? So what 4 arguments do I want to put inside of my fread function? What was the structure of?
So it's going to be the buffer, because that's the location. But would it be the address of the buffer, similar to the one that we practiced with, right? It's going to be OX25, OX50, OX44, OX46. Escape. Oh, wrong. Wint. Okay, ready first. I just forgot we don't have. So it's going to be read, and it's either going to be the buffer, and then it's gonna be, is it 4 or size of the buffer or size of signature? I'm not sure. It's gonna read from input, right? Or not, I'm not sure.
Our arguments inside of fread. Okay, so I want to read to buffer. That is my first part.
Okay, no, not
and
the
I
address.
also have a hint to myself from the comments. Read first 4 bytes. So I remember that my second argument in fread is the size, right? So I can say 1 because I know that uint
okay,
is always 1 byte.
Sorry.
Right? Or I could be more diligent and use the size of function that I was telling you about. So by using size of, I can ensure that no matter what machine I'm using, I always get the exact size of this variable, of this type. Okay, and then after the to location and the size comes the number of blocks, right? So I want to read 4 of those, and then where am I reading them?
fread. Okay.
From what is the last argument?
The input file, right?
So people already typed in the chat. Yeah, it's input, exactly. So I'm going to read it from input. Okay, let's make sure it compiles before we go any further. So make PDF, and this is where I'm going to show you why CLA is that important, right? So for example, if I try to do I get this error, right? Segmentation fault. Why is that the case? Like, why did I get an error? Okay, so someone is saying fclose. No. Yeah, so I need a value for RGB1, right? I didn't pass anything in. I only have ./pdf, but I don't actually have the file name. So when my computer gladly does what I told him to do, it gets to line 10 and it tries to open the file, but I never told him what that file was, right? I never gave it in the command line argument. So it is really important to make sure you're error checking your program correctly and that you're being a defensive programmer, right?
Okay.
You're telling your
Understand.
user
Yeah,
exactly
that's why
what you
we need
expect
the
from them. So
check.
to write my if statement, how many, what should be my value of RGC? Like how many arguments am I expecting?
3.
What condition can I set here? 2. Okay, so I can say something like, if RGC does not equal to 2, right, if they provided me with too many arguments or not enough, I want to give them a message. Please provide only one file name, right? And I want to quit. So I don't want to be going further because once again, I hit this line 14 now. My computer will try to open the file, but he can't because I never told him what this file was. All right. So let's compile this, make sure we update it, and let's run it again. And now I don't get any segmentation fault errors, and it is instead just telling me that I need to provide file name. Okay. All right, so we fread some bytes, and now let's check them, right? So essentially what I will have is the buffer array with 4 bytes of some information from my file, right? I also have my signature array of the bytes that I want to cross-check. How would I go about it, right? Like I want to compare these 4 bytes.
I forgot. Is it
something like if buffer equals to signature, then everything went well?
No.
Is that something that I could do? Okay, so yeah, people are suggesting to use a loop, and that is exactly the intuition behind it, right? I want to go comparing 1 byte at a time. So as we've seen these past weeks, we're going to set up a very simple for loop where I'm going to go until 4 because I'm only looking at the first 4 bytes. And inside my for loop, I'm just going to compare the values in each of the array 1 by 1. So I could do signature I, right, like indexing into the spot that I'm interested in. If it is not equal to the bytes that I have in buffer, what do I want to do? And I messed up this syntax here. Okay, so if I'm looking at the first value in the signature array and I'm comparing to the first value in the buffer array,
okay.
if they don't match up, what do I want to do?
Just
Exactly,
print the wrong or no, right?
Don't match up with the second or third. I don't want to go until the very end to find that out, right? I might as well just quit right away and tell my user that it's not a PDF. So I can say something like,
it's not a PDF.
Is not a PDF. New line, semicolon, and return 0. Okay, so let's make this again. Oh, typo. All right, let's make this again. Make PDF. Okay, let's try running it. And I already pre-imported some test files. So I have test GPAG and test PDF right here. So I'm going to use test PDF. Okay, I don't get anything, and I would say that's a good sign. But if I try to do PDF test JPEG, it is telling me this is not a PDF. So seems like our algorithm is indeed working as we intended, and it is telling us if it's a PDF or not. I would argue it's also nice to know if it is a PDF. So if I get through my entire for loop and I don't quit, I know it is a PDF, so I can just return this message here. It is a PDF. New line. And then lastly, I want to close my file, right? So even though I'm not necessarily seeing any errors right now in the terminal, when I run this program, odds are something might come up later, but I just want to avoid that. So I'm just going to fclose the file that I opened earlier and also return 0 to tell the program that we're done. So let's make PDF again, and let me expand this. Let me clear this first. So make PDF. Okay, let's run PDF on test PDF. Okay, nice. And then let's run it again on test JPEG. This is not a PDF. Okay. Ooh, okay, this is a lot. So let's recap this one more time now with the code that we have. So let's actually...
Oh, we have the std in. Sorry. No? Okay.
Go back to the line number 5, we actually never talked about, right? By defining this line, we are making sure that we can accept those command line arguments, right? This is our definition for doing that. Our next step is making sure that we have exactly the 2 command line arguments we were looking for. And you can go even like a little further, trying to figure out if it actually gave you a file name or something else. But this is pretty good for now. So I'm making sure that my user gives me 2 command line arguments, 1 for the program name and 2nd for the file name. If it's not indeed 2, I want to return, I want to quit. I want to end my program and tell the user that they must provide me 1 file name. My next step is now opening this file, right? Like this is the equivalent of double clicking on your file, figure out if it actually gave you a file name or something else. But this is pretty good for now. So I'm making bytes and I will give away what these hexadecimals are, but the 0x value that you see in the array are 4 hexadecimals, and 0x is telling us that they are hexadecimals. If you do some conversions, what they stand for is %PDF. So actually, there are these like hidden traces in the files that tell us exactly what they are. So really what we're doing here is something very simple. We're looking at the file sort of like on the micro level, literally looking at it byte by byte. And just by knowing this information from the internet, I know that the 4 bytes will look exactly like that. And so I can do something relatively fancy, right? Like, I don't know, if you try to open a PDF file with PowerPoint, right? Like, you won't be able to do that because it just doesn't support. Or maybe it does. Anyway, let me go back on that. If you try to open the file, right, with some program that like simply doesn't support that, one way that they can do that is like by simply checking the signature. And if it is exactly the file that they can't indeed support, they'll return an error message, which is what we're doing in this program. Okay, so line 24 is where our like juicy stuff happens. So this is where we're reading those 4 bytes of information at a time, and we're using our new functions that we just learned. So as again, fread is structured in such a way that we want to read to buffer, we want to read 4 blocks of size byte, and we want to read it from input, right? So just some order and like algorithm to it once again that you need to get used to. And then our last piece, where is like our matching up is happening, is actually quite simple, right? Like we've seen the for loops before, we've done the if statements. It is just making sure that we're comparing this information correctly, right? We want to go one index at a time, comparing 1 cell at a time at each of our arrays. I can't do if signature equals buffer, like C just can't compare things like that. And if they're indeed not equal at any point, I want to make sure I'm telling A, my user about that, and B, that I'm quitting the program, right? If my very first byte doesn't match up between the 2 arrays, there is no reason to go all the way through, right? I want to make sure they just quit right away, tell my user, and end my program. But if I indeed got through the entire for loop and I didn't quit and I didn't tell my user something like that it's not a
Hello,
PDF,
Jutastray,
I can
welcome.
success that
I'm
my
just
file is indeed a
trying
PDF.
to
And this is where
relearn
might end the
pointers
program, right?
and
Like,
memories.
I completed my goal. I either said that it was a PDF or that it wasn't, but an important step that we must take is closing the files that we opened, right? If you're coding the program similar to this, or like the one that uses fopen, literally just say, okay, I have 1 fopen here, I must have an fclose. And it is common practice to just do it in the end, but I could have also closed my finput on line 25 right here, because I technically am not using it further down in my program, but I kept it open just in case. I could if I want to access again, but once I reach to the very, very end, like literally right before I'm returning and quitting the program, I just want to close the file to make sure I'm not messing with any memory that I'm not supposed to be messing with. Okay? All right. What questions do we have about this program, about pointers, memory, before we break for the day? So someone said, could we use malloc for buffer? And we indeed can, right? We can use malloc to allocate the same amount of memory. In this case, like creating an array just because I know exactly what size it needs to be, that works as well. Okay, let's see. Someone says, does fread remember the position where it stopped the last time? Yeah, so my pointer is sort of like moving every time I fread, and this is something that will be really helpful for recover, for example, right? Like every time you read some piece of information, your arrow just keeps moving forward and you're able to read the consequent one. So someone said, can we use char star argv? Yeah, we sure can. So this is sort of like would be taking our training wheels off, and we could do char star RGV. That is just the string, but I'll keep this just for now. Okay, let me see, there's so many questions. Can I point to pointer? Yes, I can. I think someone already answered in the chat. It will just sort of be like creating this like string of things. There is no reason to do that unless you really need to, because pointers like take up space, right? When we use pointers, we're almost like doubling, if not more, the memory that we're using. So again, we want to use them exactly in the situations we need to. So do fread and fwrite only work in bytes? That's a good question. So actually, let me show an example. So if I go into manual pages.
Manual.
So let me show an example. If we go into manual pages and I open fread, I can read the description.
Closing SF seems like a good idea to me. C++ and other languages have ways to make sure it happens at some point, but in C, you're responsible for doing things. Yeah. I'm just trying to really learn the very, very basic again before I forgot and just kind of like failed another interview. So kind of really want to make my fundamentals stronger again. So yeah, here I am.
where under the size, and let me zoom in here a little bit. So under the size component, it says which is the size in bytes of the data.
So it has to be
so
bytes.
This is just how Freed is set up, and you'll actually find that the two, sort of like the size and the number, can be interchangeable depending on the situation. But yeah, we want to make sure we're specifying it in bytes. And the easiest way to go about it is just using the size off function, right? That will always return exactly the size of the data type that we're looking for. Okay, let's see. There's so many more questions. Can we close the file input inside the loop? Yeah, we sure can. But consider the case if we don't get to this part, right? If we try to fclose here, we might never, like if it is exactly like PDF, we might never reach that point. So you always want to make sure that you're closing the file, like not inside the if statement or like somewhere where your code might not reach, but just doing it in the very end is a good habit to get into. Okay. So the usage for the program, someone asked in the chat, is ./pdf and then the name of the file. So in this case, I use test.pdf. And you just want to make sure you have those files in your environment.
Yeah, I don't have it, so I couldn't really test it. But
you'll also get an error.
Never mind then.
Okay. Let's see. So why do we return 0 when we already closed the file? So this is going back to the previous week, right, where we talked about the main function a little bit. So in my definition of the main function, I say int main and then whatever arguments I'm accepting. By saying int main, I am specifying that the return type of my main function has to be like a number, an integer. So in this case, I am like returning 1 when I want to terminate on line 11 if I didn't get the correct number of arguments. Or here, I am also returning 0 and returning 0 here. You could, again, write different numbers. It doesn't really matter. I could write 4, but 0 is for a successful program. And even if it's not a PDF, right, like our program was still successful. It identified what kind of file it is, or rather, if it was a PDF or not. So it was still a success. So we can return 0 here and then 0 in the very end. Alrighty.
Okay, is there like a way I could practice it? Like the problem set, right? Okay, let's try. Pointer arithmetic? Oh, okay. Oh, this is how the like arrays work, right? P plus 1 is the, yeah, this is how like arrays actually made, right? Oh god, it's a double pointer. Okay, let's see if there's another like. We already have sub volume. Let's try this version of filter. Let's see. Although I'm not entirely sure I could, but we're here to try. Okay. Perhaps the simplest way to represent an image is with a grid of pixels, each of which can be of a different color. For black and white images, we thus need 1 bit per pixel, as 0 could represent black and 1 could represent white. In this sense, then, is an image just a bitmap? For more colorful images, you simply need more bits per pixel. Uses 24 bits per pixel, so there would be like 24 smaller squares inside of this, I would assume. 24 bits uses 8 bits. 4 bits to signify the, okay, I see. Oh, yeah, okay. And 8 bits to signify the blue. If you've ever heard of RGB, well, there you have it. If the RGB and values of some pixel are, say, this in hexadecimal, that pixel is purely red. Holy, is it? Wait. Oh my god, okay, it is. If it's... Wait, there's a easier one? Which one is it? Which one is the easy one? Which one is like the easy one? I don't. Oops. Okay, never mind. Yeah, I want the easy one. Where's the easy one? Where's the easy one? Is it recover? Since n needs to be row bytes and doesn't take size of the elements into account, just do something like, okay. Wait, which one is the easy one? I don't see it. You know what? I'm just gonna find it like practice question for pointers. I don't. Okay, whatever this is. Okay, let's try it. Whoa. Okay, 110. Okay, got it. It includes time size which can be solution data expansion for related problems. Okay. Let's see the basic declaration pointer. Okay. Hello. The easy one is the blur filter, while the hard one is edge filter. Okay. Let's try a lot of this practice and then we go back there because it's already a bit too late. Recover? Okay, which one is it? I'm confused. This one, right? Holy. Oh, it's just the one that I read. Okay. Which one is the easy one first, man? Like, calm down, calm down. Isn't it super known term in CS, but it's a good word to explain very common structure. The dynamic. Hello, red bottle shorts. Dynamic allocated I-leaves or strings is an example. I often end up doing practice example. How about it? Ilife? How do you like say it? Is that correct? Isn't a super known term, but it's a good word to explain a very common structure. Ilife? I-life? Ilife. Is it? Okay, never mind. Okay, do I just like int m equals 10. N and O are two integer variables. Okay, so we can do N and O, but we don't set anything. And then we have int Z, which is equals to the address of M. Right. Yeah. Oh, source address. Sources. Okay. Is this correct? Oh, you need to print it. Okay, I didn't. The instruction wasn't very clear, but yeah, it's correct, right? Oh, okay. We can just do this. I thought like okay, yeah, we need to print it. Okay, like okay. Let's set this right. Sorry. Okay. Let's try the recover then. Which one is this one? Recover. Elif. It's after a person, so I'm not sure. Okay, so it's elif. Okay, let's try recover. Although I'm not entirely sure. This is actually pretty good. I like it. It's a bit too simplistic, but okay, let's try recover, yeah? In the general of this problem, we spent the past several days taking photos around campus, all which were saved on a digital camera as JPEG. Having an array of pointers to array. Sorry for my tangent. No, it's fine. I'm just trying to piece together the point that you make. sorry. No worries. Okay, let's unzip them. Sorry. And then we can just recover. Yeah. CD to, is it recover? Yeah. art.raw and we have recover.c. I hope I'm not speaking too loud. I don't want to annoy my mates. I'm so sorry if I scream. So I'm gonna try to speak more calmly this time. Okay. Oh wow, really? So say the first 3 byte. Oh, it's similar to the problem. We have the 3 byte. Factor and array are basically synonyms in C. I see. Okay. I see. Stop with the C puns. Sorry. I just can't keep. Sorry. I want to make another memory joke, but I ran out of. Sorry. Never mind. It's funny on my head. Okay. Never mind. I'm gonna stop. In the context of CD overlap. Factoring math and array and yeah, true. I understand that. Yeah. Because like for example, like factor in linear algebra is just like 2-dimensional arrays or 3-dimensional arrays, right? So it's just like, okay. Or yeah, something. I don't know. To be honest, the dynamic allocation part is not that much. I haven't really done that much because this is still like the basics of it. So far it's only been just like pointers and normal like memory malloc stuff, but not that I haven't done much practice and any like more complex usage beyond that. So this is really me relearning it again because I think when I took the course in college, I don't really like remember a lot anything to be exact. So this is like actually relearning it again. Yeah, I did. I missed 4 days because I need to get a new monitor because it is. I mean, it's possible to use only the main laptop, but I couldn't, so I kind of need to look for like a second-hand, cheaper monitor. So basically, I need. I didn't have a second monitor, so I need to find a good deal from Kleinanzeigen or like eBay, basically. So that's why I didn't do it for 4 days. It's such a terrible excuse, I know, and I'm sorry, but here I am again. I'm back. If it's until 50, that means the first image is that, so it's gonna be 049 the JPEG, right? Yes. So I can have one for OBS and the other for the actual stuff because I've tried using only one and it's not that good. Like it's just overlapping, confusing. It's just not that nice. It's such a terrible excuse. I just really want. Never mind. Forget about it. Okay. To be honest, I don't really understand the creating the memory part. No. It was borrowed, to be honest. It was my friend's monitor, and he was out of town, so he went back and he wanted to use it, so I cannot use that anymore. That's why. Okay. Let's just follow the instruction. Although we don't have, at least we don't have Copilot help using actual Vim. So we have if argc is not 1. Huh? I see. It's not 2. Sorry, it's not 1. It's going to print out. What is it? What does the usage mean? So it's gonna do a f open. Or do we need to create buffer? Okay. Is it? Okay. Yeah, no, yeah, it was my friend's monitor and I was borrowing it. So, yeah, right now I have my own. I would say it's a pretty good deal. I would say. It was quite old, but it still works. So, all good. Okay, okay. So we're gonna use while loop again, similar to like the reading PDF. Now, okay, how does you create the JPEG? That's okay. Normal full stack? Oh, I kind of want to start with the basics again. Like, I think I'm gonna try to do some vanilla stuff after this. After like the data structure, I wanna do like some vanilla stuff because I guess I've been in high level language too much. It's time to start getting low and redo the basics. So I think after this the test, I'm gonna do the week 5, which is the algorithm. The data structure, and after that I'm gonna try to redo vanilla stuff because I guess I just don't get or like forgot a lot of the basics. And during my last interview, I kind of I couldn't really explain some of the basic stuff in a proper way. Like, I know what it is in my mind, but I couldn't articulate it, or I couldn't really explain it to the recruiter, and that felt like crap. That felt terrible. So yeah, I kind of really just want to relearn everything from the basic again so that I could get the fundamentals right, so that I know it's stupid, I know it's terrible that the recruiting process has to be that way, but either way I gotta really, yeah, I did, but I failed, so that's why I'm redoing everything from the ground up again, so that I would be able to answer those questions, even though it probably would be depending on the company. But yeah, definitely do not want to experience that anymore. I think it was like last month, I think. But I'm still doing some full stack project on the side. Like, it's just that I didn't stream that part. I have one project to migrate a website, but that was for that it is using React and Hono, but it's still in progress. But I didn't stream that because I prefer doing this for the stream, and maybe later I will have to update some of my projects. I've already updated some of the projects, but not all. So I think I want to do the project, of course, later. So yeah, basically I just don't want to feel like crap where I couldn't really understand basic topics during interview. So here I am. Can we cat the Oh, we can. Okay. Okay, but I have no idea what this is all about. What are those symbols, man? This is crazy. Wait, maybe if we have Yahtzee, can we install Yahtzee on WSL for like the file viewers? Let's try to add Yahtzee because I heard it's a very cool terminal. Okay. Maybe, I don't know. Can we installation for WSL? Cache, homebrew, MacBook, Windows. Fedora, Flatpak, Ubuntu, no? You can install the optional dependencies with Note that these dependencies are quite old. Okay, it's not available on Ubuntu, sadly, but okay. It's okay, can't problem, okay. I guess this is just a binary file or like okay, how do you generate it based on that into like a JPEG? That wasn't a, yeah, it's a raw file, right? But how do I like grab those? Keep in mind that you can open CardDraw programmatically with open as with below. Machine code, really? Okay, now that you've checked it. You should, of course, check to be sure the file was opened properly. If it wasn't, tell user it will leave this. Okay, so definitely, right? We need to create if card equals to null. Okay, but I want to just to make sure that it is correct. If you have not ever used Java and look at the compiled file, it's similar. Ah, okay, one step before binary. Okay. Okay, I'm gonna ask GPT for this. Sorry, I know you're trying to use AI. Okay. How to properly. Okay, so yeah, it's correct. So if the it's gonna return 1. Okay. Okay, so almost correct. Okay, this part I don't understand how, or like I don't know how. Along the way, your program should recover every one of the JPEGs from card raw, storing each as a separate file in your current working directory. First, consider how to read card raw away. Recall that to read data from a file, you need to temporarily store the data in a buffer. And recall further that stores data in blocks of 112 bytes. As such, you likely want to create a buffer of 112 bytes to store blocks of data as you read them sequentially. One way of doing so is to use the uint80 type from stdint. Okay, so we need to... Oh. stdint. So we need to do stdint, stdio, and stdlib. Okay. So how do we generate them files? That's the part I want to do. So is to use per its manual page, F-read returns the number of bytes that it has read, in which case it should return 112 or 0, given that it's a number of blocks. In order to read every block after opening it, it should suffice to using a loop like this. Okay, yeah, please tell me, how do we convert those raw files into images? Number the files. Okay, numbering the files. I mean, we could just use for loop. Can we use for loop? Like while, or it's inside the while loop and then printed name based on ith index based on the division of the binaries into those images. Okay, you know, let's watch the walkthrough, man. I'm confused.
In Recover, we've taken a memory card from a camera and accidentally deleted all of the images. Your task is going to be to write a program to recover those images, generating new JPEG files for each. How are you going to do that? Well, first, you're going to want to open the memory card file that we'll give to you. Then, you're going to look through that memory card, which will take as its first parameter the name of a file you want to open, and the second parameter represents what mode you want to open it in, where R stands for read mode, where you want to read information from that file. As you're reading that file, though, you're going to want to be on the lookout for JPEGs. How are you going to know
this file gets converted to binary? Ah, okay. But it's a raw file.
The first byte of every JPEG file is OXFF in hexadecimal. The second byte is always OXD8. The third byte is always OXFF.
Do we need to use the string compare?
But it's always OXE0 or OXE1 or OXE2, anything that starts with OXE and then something. So it could be OXEF, for example. These are all valid JPEG headers. So if you notice this pattern of 4 bytes at the beginning of any 512-byte block, you can pretty safely assume it's the beginning of a JPEG file. So let's talk in a little bit more detail about JPEGs. Each JPEG is going to start with a distinct header, where the first 3 bytes, as we've talked about, are OXFF, OXD8, and OXFF. And the last byte is OXE0 or OXE1 or OXE2, anything up to OXEF. So this is the header that you're going to be looking for. And we'll tell you that each of the JPEGs are stored back-to-back in the memory card. After one JPEG ends, the next one begins, and so on and so forth, up through the end of the file, inside of these 512-byte blocks. So what does this mean for how you can look through this memory card to try to find JPEGs? Well, if you imagine your memory card as a whole bunch of these 512-byte blocks, then what you can do is start at the first block of the JPEG file and check to see if you found a JPEG header or not. If you haven't found a JPEG header, you'll keep moving on, looking one block at a time, until you find that sequence of 4 bytes that indicates to you that this block is the beginning of a JPEG file. Once you find that block, now you can open up a new JPEG file that you're going to start writing to, and you can start writing block after block after block as you find more and more blocks of this JPEG file. What you'll run into eventually, though, is another block where the first 4 bytes also look like the start of a JPEG file. And when you detect that, you should realize that this is probably the start of a new JPEG file, meaning you should close the old one, you're done writing to it, and start writing to a new JPEG file that has all of these next sequences of blocks as the data within it. So you continue writing again and again, and you'll repeat this process, looking through this file until you find the start of another JPEG file, then starting to write that new file, and repeating that process again and again and again until you reach the end of the memory card, at which point you'll have found all of the JPEG files that are inside of this memory card. How are you going to read data, though, from the memory card? Well, to do that, you can use the fread function, which takes 4 parameters. The first parameter is called data, and it is going to be a pointer to where you're going to store the data that you're reading, likely some buffer of some kind that might be an array, for example. Next is size.
Hello? Hi. How are you? Good, how are you? Good, also. Yeah, did you start the university? No, not yet. Do you need any help? Yeah, I know. What's the big one? Oh my, oh, the big one. My friend before me. Do you need it? Do you want me to take it? I think she finished at this one. Okay, let me get it. Oh, okay. All right. He's the one that lives in the. One moment. Sorry, need to pick up something.
Which is the number of bytes of each element that you're going to try to read from the file. Next up is number, which is the number of those elements that you want to try to read all at once. And then finally is inpointer, which is the file that you're going to actually read that data from. And recall that what you want to do is read from the memory card file in 512-byte chunks. Once you've read one of those 512-byte chunks, though, how are you going to know if that 512-byte chunk is actually the start of a JPEG file or not? Well, recall that the JPEG file has a distinct header. So if you've read this 512-byte block into some sort of buffer, which might be an array of bytes, then what you can do is check. To see if buffer square bracket 0, in other words, the first byte of the buffer, is OXFF, the first byte of a JPEG file. And likewise, you can do the same thing, checking if the second byte in the buffer is OXD8 and the third byte in the buffer is OXFF. The fourth byte is where things get a little bit tricky. Recall that there are 16 different values that buffer square bracket 3
Okay, so it doesn't, it's not just as simple if.
Take on. It could be OXE0 or OXE1, so on and so forth. And so what you might imagine doing as a first pass is a Boolean condition, where you ask yourself if buffer 3 is OXE0, or buffer 3 is OXE1, or OXE2, or OXE3, or OXE4, so on and so forth. But doing this 16 times is going to get very, very tedious. So to simplify, we can use a trick known as bitwise arithmetic, where I can take the bitwise AND of buffer 3 and OXF0. What that's going to do is it's going to say, just look at the first 4 bits of this 8-bit byte and set the remaining 4 bits to 0. What that means is that OXE0, OXE1, OXE2, so on and so forth, all become OXE0 because we've cleared out those last 4 bits. Then, after we've done this bitwise AND, we can just compare the result to OXE0 to determine whether or not this byte is a byte that might appear as the 4th byte inside of a JPEG. If all of these conditions are true, it's pretty likely that the 512-byte block that you found represents the beginning of a new JPEG file. So when you found the beginning of a new JPEG file, what you'll need to do is create a new file where you're going to write this data to. How do you make a new JPEG file? Well, each file should have a very particular file name, as digit.jpg, starting with 000.jpg in the order in which you find it. So you'll likely want to keep track of how many JPEGs you found so far so that you can write the correct file names in the correct order. How do you create a string of the format digit.jpg? Well, to do this, you can take advantage of a function called sprintf, where you're printing not to the terminal, but to a string, where the first parameter is the name of the string you want to write to, in this case, file name. The second parameter is the format string, %.
How is it in the progress? Sorry, I need to grab something.
Because we've cleared out those last 4 bits. Then, after we've done this bitwise AND, we can just compare the result to OXE0 to determine whether or not this byte is a byte that might appear as the 4th byte inside of a JPEG. If all of these conditions are true, it's pretty likely that the 512-byte block that you found represents the beginning of a new JPEG file. So when you found the beginning of a new JPEG file, what you'll need to do is create a new file where you're going to write this data to. How do you make a new JPEG file? Well, each file should have a very particular file name, as digit.jpg, starting with 000.jpg in the order in which you find it. So you'll likely want to keep track of how many JPEGs you found so far so that you can write the correct file names in the correct order. How do you create a string of the format digit.jpg? Well, to do this, you can take advantage of a function called sprintf, where you're printing not to the terminal, but to a string, where the first parameter is the name of the string you want to write to, in this case, file name. The second parameter is the format string. %03i just means print an integer with 3 digits to represent it, even if a number like 0 or 1 or 2 doesn't really require 3 digits to print out that integer.
And what's the second parameter? The third?
And the final parameter is the number that you want to substitute. In this case, 2, where the result would be that the file name string would now contain 002.jpg instead. Make sure that file name, though, has enough memory or has enough characters to fully represent this entire file name. after you've created the file name, you can open a new file with that file name by calling fopen again, this time providing as the first argument the name of the file you want to open. And now the second argument to fopen, instead of R for read, is going to be W for writing. So that you can begin to write to this new file all of the data that you're going to find from the memory card. How do you write data to a file? To do that, you can use the inverse of fread, which is fwrite, which is going to write data to a file. Fwrite, just like fread, also takes 4 parameters. The first parameter, called data, is going to be a pointer to all of the bytes that you want to write to the file. Next, you need to tell fwrite how big the elements that you're going to write are. So the second parameter, size, represents the number of bytes in each element that you're going to write to the file. Next is number, the number of elements that you're going to write to the file. And finally, outPointer is the file pointer that you actually want to write the data to, likely the JPEG that you've just opened for the purpose of writing to it. And you're going to continue doing this, writing data to JPEG after JPEG until you reach the end of the file. But how do you detect when the end of the file is? Well, to do that, let's take another look at fread, which is the function that we're using in order to read data from the memory card that's given to you at the beginning of the program. What does fread return? Well, it turns out that fread returns the number of items of size that were read. We currently try to read number elements of size, and so most likely, if fread is able to read all of that data, it's going to return back to you number. Say that I'm trying to read 255 elements, for example, then fread is going to return to me 255. Of course, once I reach the end of the file, it might be the case that I don't have 255 additional bytes to read, and I have fewer than that. In that case, fread is going to return to me some number that is less than 255. So you might want to think about what condition you could write to determine whether fread has gotten to the end of the file or not. Let's put all of this together now and start to think about some pseudocode that you could use to implement this recover program. The first thing you'll want to do is open the memory card. Then after that, you're going to want to repeat some process until you reach the end of the card. You'll want to read 512 bytes, likely using fread, into some sort of buffer, some space in your computer's memory where you have 512 bytes worth of storage that you can read that data into. Then take a look at the 512 bytes that you've read. If it's the start of a new JPEG, which you can detect by looking at those first 4 bytes and determining whether or not it's a JPEG header or not, then you know you found a new JPEG. So if this is the first JPEG, you should start writing 000.jpg and start writing your very first file. Of course, if you've already found a JPEG, then you'll need to make sure to close the file you've just been writing to so that you can open up this new file that you're going to continue writing to. So that's what to do if the 512 bytes you read is the start of a new JPEG. But if it's not the start of a new JPEG, what should you do then instead? Well, if you've already found a JPEG and you've already been writing to it, then you should keep writing to it. This is the next 512 byte block of this current JPEG that you've been writing to. And you might repeat this process multiple times because every JPEG might take up multiple blocks of memory inside of the memory card that we've given to you. So you'll repeat this process, reading 512 bytes, and then checking. If it's the start of a new JPEG, you might need to do something. If it's not the start of a new JPEG, you might need to do something else. After you've reached the end of the memory card, then you should close any remaining files, and if all goes well, you should be done. And you should see that you've now generated a number of JPEG files, each of which contains image data that you can then open up and view visually. My name is Brian, and this was Recover.
I still don't understand, to be honest. Okay.
Inside of a JPEG. If all of these conditions are true, it's because we've cleared out those last 4 bits. Then, after we've done this bitwise AND, we can just compare the result to OXE0 to determine whether or not this byte is a byte that might appear as the 4th byte inside of a JPEG. If all of these conditions are true, it's pretty likely that the 512 byte block that you found represents the beginning of a new JPEG file. So when you found the beginning of a new JPEG file, what you'll need to do is create a new file where you're going to write this data to. How do you make a new JPEG file? Well, each file should have a very particular file name, as digit.jpg, starting with 000.jpg.
Okay, let's just try it. So if
in the order in which you find it. So you'll likely want to keep track of how many JPEGs you found so far so that you can write the correct file names in the correct order. How do you create a string of the format digit, digit, digit.jpg? Well, to do this, you can take advantage of a function called sprintf, where you're printing not to the terminal, but to a string, where the first parameter is the name of the string you want to write to, in this case, file name. The second parameter is the format string. %03i just means print an integer with 3 digits to represent it, even if a number like 0 or 1 or 2 doesn't really require 3 digits to print out that integer. And the final parameter is the number that you want to substitute, in this case 2, where the result would be that the file name string would now contain 002.jpg instead. Make sure that file name, though, has enough memory or has enough characters to fully represent this entire file name. After you've created the file name, you can open a new file with that file name by calling fopen again, this time providing as the first argument the name of the file you want to open. And now the second argument to fopen, instead of R for read, is going to be W for write it, so that you can begin to write to this new file all of the data that you're going to find 02.jpg in the terminal format of how many JPEGs you found so far. How do you make a new JPEG file? Well, each file should have a very particular file name, as digit, digit, digit.jpg, starting with 000.jpg in the order in which you find it. So you'll likely want to keep track of how many JPEGs you found so far so that you can write the correct file names in the correct order. How do you create a string of the format digit, digit, digit.jpg? Well, to do this, you can take advantage of a function called sprintf, where you're printing not to the terminal, but to a string, where the first parameter is the name of the string you want to write to, in this case, file name. The second parameter is the format string. %03i just means print an integer with 3 digits to represent it, even if a number like 0 or 1 or 2 doesn't really require 3 digits to print out that integer. And the final parameter is the number that you want to substitute, in this case 2, where the result would be that the file name string would now contain 002.jpg instead. Make sure that file name, though, has enough memory or has enough characters to fully represent this entire file name. After you've created the file name, you can open a new file with that file name by calling fopen again, this time providing as the first argument the name of the file you want to open. And now the second argument to fopen, instead of R for read, is going to be W for write it, so that you can begin to write to this new file all of the data that you're going to find from the memory card. How do you write data to a file? To do that, you can use the inverse of fread, which is fwrite, which is going to write data to a file. Fwrite, just like fread, also takes 4 parameters. The first parameter, called data, is going to be a pointer to all of the bytes that you want to write to the file. Next, you need to tell fwrite how big the elements that you're going to write are. So the second parameter, size, represents the number of bytes in each element that you're going to write to the file. Next is number, the number of elements that you're going to write to the file. And finally, outPointer is the file pointer that you actually want to write the data to, likely the JPEG that you've just opened for the purpose of writing to it. And you're going to continue doing this, writing data to JPEG after JPEG until you reach the end of the file. But of the buffer is OXF values that buffer square bracket 3 could take on. It could be OXE0. If the second buffer, which might be an array of bytes, then what you can do is check to see if buffer square bracket 0, in other words, the first byte of the buffer, is OXFF, the first byte of a JPEG file. And likewise, you can do the same thing, checking if the second byte in the buffer is OXD8 and the third byte in the buffer is OXFF. The fourth byte is where things get a little bit tricky. Recall that there are 16 different values that buffer square bracket 3 could take on. It could be OXE0 or OXE1, so on and so forth. And so what you might imagine doing as a first pass is a Boolean condition, where you ask yourself if buffer 3 is OXE0, or buffer 3 is OXE1, or OXE2, or OXE3, or OXE4, so on and so forth. But doing this 16 times is going to get very, very tedious. So to simplify, we can use a trick known as bitwise arithmetic, where I can take the bitwise AND of buffer 3 and OXF0. What that's going to do is it's going to say, just look at the first 4 bits of this 8-bit byte and set the remaining 4 bits to 0. What that means is that OXE0, OXE1, OXE2, so on and so forth, all become OXE0 because we've cleared out those last 4 bits. Then, after we've done this bitwise AND, we can just compare the result to OXE0 to determine whether or not this byte is a byte that might appear as the 4th byte inside of a JPEG. If all of these conditions are true, it's pretty likely that the 512-byte block that you found represents the beginning of a new JPEG file. So when you found the beginning of a new JPEG file, what you'll need to do is create a new file where you're going to write this data to. How do you make a new JPEG file? Well, each file should have a very particular file name, as digit, digit, digit.jpg, starting with 000.jpg in the order in which you find it. So you'll likely want to keep track of how many JPEGs you found so far so that you can write the correct file names in the correct order. How do you create a string of the format digit.jpg? Well, to do this, you can take advantage of a function called sprintf, where you're printing not to the terminal, but to a string, where the first parameter is the name of the string you want to write to, in this case, file name. The second parameter is the format string. %03i just means print an integer with 3 digits to represent it, even if a number like 0 or 1 or 2 doesn't really require 3 digits to print out that integer. And the final parameter is the number that you want to substitute, in this case 2, where the result would be that the file name string would now contain 002.jpg instead. Make sure that file name, though, has enough memory or has enough characters to fully represent this entire file name.
Yeah, this one I don't understand. Okay. What do you? Oh, okay. Okay. No, I don't understand. How should we do this actually? Do we use a for loop to create? Why does it? The example shows 2 and it becomes 002. Like what is that supposed to mean? Okay. Like in this case of file name, is it, do we create like a new variable, or
0 or string digit.jpg? Well, to do this, you can take it back through. Well, each file should have a very particular file name, as digit.jpg, starting with 000.jpg in the order in which you find it. So you'll likely want to keep track of how many JPEGs you found so far, so that you can write the correct file names in the correct order. How do you create a string of the format digit.jpg? Well, to do this, you can take advantage of a function called sprintf, where you're printing not to the terminal, but to a string, where the first parameter is the name of the string you want to write to, in this case, file name. The second parameter is the format string. %03i just means print an integer with 3 digits to represent it, even if a number like 0 or 1 or 2 doesn't really require 3 digits to print out that integer. And the final parameter is the number that you want to substitute, in this case 2.
what does the 2 mean? I don't.
Where the result would be that the file name string would now contain 002.jpg instead. Make sure that file name, though, has enough memory or has enough characters to fully print an integer with 3 digits to represent it, even if a number like 0 or 1 or 2 doesn't really require 3 digits to print out that integer. And the final parameter is the number that you want to substitute, in this case 2, where the result would be that the file name string would now contain 002.jpg instead. Make sure that file name, though, has enough memory or has enough characters to fully represent this entire file name. After you've created the file name, you can open a new file with that file name by calling fopen again, this time providing as the first argument the name of the file you want to open. And now the second argument to fopen, instead of R for read, is going to be W for write it, so that you can begin to write to this new file all of the data that you're going to find from the memory card. How do you write data to a file? To do that, you can use the inverse of fread, which is fwrite, which is going to write data to a file. Fwrite, just like fread, also takes 4 parameters. The first parameter, called data, is going to be a pointer to all of the bytes that you want to write to the file. Next, you need to tell fwrite how big the elements that you're going to write are. So the second parameter, size, represents the number of bytes in each element that you're going to write to the file. Next is number, the number of elements that you're going to write to the file. And finally, outPointer is the file pointer that you actually want to write the data to, likely the JPEG that you've just opened for the purpose of writing to it. And you're going to continue doing this, writing data to JPEG after JPEG until you reach the end of the file. But how do you detect when the end of the file is? Well, to do that, let's take another look at fread, which is the function that we're using in order to read data from the memory card that's given to you at the beginning of the program. What does fread return? Well, it turns out that fread returns the number of items of size that were read. We currently try to read number elements of size, and so most likely, if fread is able to read all of that data, it's going to return back to you number. Say that I'm trying to read 255 elements, for example, then fread is going to return to me 255. Of course, once I reach the end of the file, it might be the case that I don't have 255 additional bytes to read, and I have fewer than that. In that case, fread is going to return to me some number that is less than 255. So you might want to think about what condition you could write to determine whether fread has gotten to the end of the file or not. Let's put all of this together now and start to think about some pseudocode that you could use to implement this recover program. The first thing you'll want to do is open the memory card. Then after that, you're going to want to repeat some process until you reach the end of the card. You'll want to read 512 bytes, likely using fread, into some sort of buffer, some space in your computer's memory where you have 512 bytes worth of storage that you can read that data into. Then take a look at the 512 bytes that you've read. If it's the start of a new JPEG, which you can detect by looking at those first 4 bytes and determining whether or not it's a JPEG header or not, then you know you found a new JPEG. So if this is the first JPEG, you should start writing 000.jpg and start writing your very first file. Of course, if you've already found a JPEG, then you'll need to make sure to close the file you've just been writing to so that you can open up this new file that you're going to continue writing to. So that's what to do if the 512 bytes you read is the start of a new JPEG. But if it's not the start of a new JPEG, what should you do then instead? Well, if you've already found a JPEG and you've already been writing to it, then you should keep writing to it. This is the next 512 byte block of this current JPEG that you've been writing to. And you might repeat this process multiple times because every JPEG might take up multiple blocks of memory inside of the memory card that we've given to you. So you'll repeat this process, reading 512 bytes, and then check it. If it's the start of a new JPEG, you might need to do something. If it's not the start of a new JPEG, you might need to do something else. After you've reached the end of the memory card, then you should close any remaining files, and if all goes well, you should be done. And you should see that you've now generated a number of JPEG files, each of which contains image data that you can then open up and view visually. My name is Brian. A number of already found a JPEG, and you could write to determine whether fread has gotten to the end of the file or not. Let's put all of this together now and start to think about some pseudocode that you could use to implement the file. Now open enough memory or has enough characters to fully represent this entire file name. After you've created the file name, you can open a new file with that file name by calling fopen again, this time providing as the first argument the name of the file you want to open. And now the second argument to fopen, instead of R for read, is going to be W for writing, so that you can begin to write to this new file all of the data that you're going to find from the memory card. How do you write data to a file? To do that, you can use the inverse of fread, which is fwrite, which is going to write data to a file. Fwrite, just like fread, also takes 4 parameters. The first parameter, called data, is going to be a pointer to all of the bytes that you want to write to the file. Next, you need to tell fwrite how big the elements that you're going to write are. So the second parameter, size, represents the number of bytes in each element that you're going to write to the file. Next is number, the number of elements that you're going to write to the file. And finally, out pointer is the file pointer that you actually want to write the data to, likely the JPEG that you've just opened for the purpose of writing to it. And you're going to continue doing this, writing data to JPEG after JPEG until you reach the end of the file. But how do you detect when the end of the file is? Well, to do that, let's take another look at fread, which is the function that we're using in order to read data from the memory card that's given to you at the beginning of the program. What does fread return? Well, it turns out that fread returns the number of items of size that were read. We currently try to read number elements of size, and so most likely, if fread is able to read all of that data, it's going to return back to you number. Say that I'm trying to read 255 elements, for example, then fread is going to return to me 255. Of course, once I reach the end of the file, it might be the case that I don't have 255 additional bytes to read, and I have fewer than that. In that case, fread is going to return to me some number that is less than 255. So you might want to think about what condition you could write to determine whether fread has gotten to the end of the file or not. Let's put all of this together now and start to think about some pseudocode that you could use to implement this recover program. The first thing you'll want to do is open the memory card. Then after that, you're going to want to repeat some process until you reach the end of the card. You'll want to read 512 bytes, likely using fread, into some sort of buffer, some space in your computer's memory where you have 512 bytes worth of storage that you can read that data into. Then take a look at the 512 bytes that you've read. If it's the start of a new JPEG, which you can detect by looking at those first 4 bytes and determining whether or not it's a JPEG header or not, then you know you found a new JPEG. So if this is the first JPEG, you should start writing 000.jpg and start writing your very first file. Of course, if you've already found a JPEG, then you'll need to make sure to close the file you've just been writing to so that you can open up this new file that you're going to continue writing to. So that's what to do if the 512 bytes you read is the start of a new JPEG. But if it's not the start of a new JPEG, what should you do then instead? Well, if you've already found a JPEG and you've already been writing to it, then you should keep writing to it. This is the next 512 byte block of this current JPEG that you've been writing to. And you might repeat this process multiple times because every JPEG might take up multiple blocks of memory inside of the memory card that we've given to you. So you'll repeat this process, reading 512 bytes, and then check it. If it's the start of a new JPEG, you might need to do something. If it's not the start of a new JPEG, you might need to do something else. After you've reached the end of the memory card, then you should close any remaining files.
Is it a recursion? Okay, I give up. I don't know. I don't know how to do it. Oh, okay. This is just creating the byte type, right? Okay. So I wouldn't really need to write this over and over. Just the byte and yeah, yeah. Okay. Um, byte buffer, that buffer. Yeah. Okay. That's actually a much better way to do it. Agree. Oh, okay. I don't know what this is. Okay. So we still need to somehow store the count of the JPEG. Okay, we did close out pointer. Okay, I'm just following it because okay, if output equals null, f close output spring f 3D. Okay, so this is that's why. Okay, he uses this because this is gonna change, right, every single time. That's actually clever. Okay, yeah, I wouldn't have thought about it at all. With the JPEG plus plus thing. Okay. Close out if JPEG was found before and returned. Yeah, since using this like increment, it's still going to after its returns. That's going to be well, yeah. Close less open. Okay. Okay, I'm gonna try to redo it one by one. Like I'm gonna redo it, okay? I still don't understand it, but okay. Let me just okay, we can't do that. Yes, because I don't understand at all how does this work. Okay. So it just creates it. The only part that I don't that I miss and understand is that this I need this count, and I don't really understand like the nested here. Open a new pointer for writing. Okay, so the while loop okay. Uh okay, maybe what can we like improve for our own code? So that is already correct. If card is null, could not be open. Okay. Can return another. That is correct. set out file pointer out file. So out file should be the file name. So sure file name. Okay, so this is incorrect, but I should create this first. Why is that? Isn't that just the same? This is the same, right? But okay, so we still need to have the file name is okay. My way of thinking this is correct, but why is it like that? If buffer, okay, my buffer is, it's basically the same. If out pointer is null, out pointer is the image, right? Okay, so why can we not, why do we like, okay. Can we not do that? Okay, I'm gonna try to do it this way. But then I couldn't really do it. Oh, okay. So read this is reading the 500. If it starts a new, there should be another one. If it's the first JPEG, that's why we need to create this first so that inside of here it wouldn't be empty, but so we should actually okay. This is to store inside of the sprintf. Okay, we should actually have the file image equals to null. So we want to have the pointer created, but we want to point it at null first because we will be needing it to check, yeah, if it was like found before or not. Okay, if okay, yeah, it's if close, and if not, we're gonna sprint. But instead of, it's not 2, but it's the JPEG plus plus. Okay. So it's actually not here. Well, at least you know it works, but okay, I still really don't understand how that works. Or like yeah, I'm gonna need to find a way or ask AI to explain like what the fuck, how is that work, or like what. Yeah, that's it. I'm going to bed. It's already almost midnight, so I'm just gonna see you, if not tomorrow, in 2 days or in any other days. I'm not entirely sure. Huh, okay. Yeah, we can do one. Okay, at least it worked, but I there's still a lot of things that I'm not entirely sure. The thing is, I kind of I'm able to do 50% of it, but the other 50 to do the main thing, I I I don't know how to reach this level of like okay, let's like try it another practice later, but okay, it is what it is. See you guys some other time.